giving us ideas.
I'm just making up stuff.
Alright.
Similar to your notes. So we'll do x cubed plus 4x squared minus 5. That looks like similar to what we're doing with. I just looked at your notes. That's too close. We'll go negative x cubed plus 2x squared minus x plus 1. Alright. So we want to find where the function is increasing, decreasing. We want to find extrema. We want to find where it's concave up, where it's concave down, or if there's inflection points. Alright, we don't know how to do all this stuff yet. Okay, so we should talk, what's the first thing you suppose you should do? Find the derivative. Alright, so f prime is 3x squared plus 4x minus 1.
I couldn't figure out how to send it to you, Kyle, sorry.
Alright, so let's set that equal to 0. And somebody quad it, please.
6.
Point 3 and 1.
Really?
131.
1/3 and 1?
Yeah.
I knew that.
Height.
It's gonna work out to be rational. Okay, so we have two potential extreme points. So we could analyze to the left and the right of 1/3 and the left and right of 1. We could use our first derivative test. So if I found out what f prime of 0 is, what is it?
-1.
It's -1. What does that tell me the function is doing as it gets close to 1/3? So it's decreasing. So at 0 it's decreasing. Then we know it gets to 1/3. So we could verify afterwards between 1/3 and 1. I'll say f prime of 1/2. We could plug that in. We get -3/4 plus 2 is 1 1/4. So I get 1/4. So I know it is increasing at 1/2, which is between those two. And then we could find f prime of like 2. What do you think that's going to give you? Positive or negative?
Positive.
Negative.
So it decreased, then it increased, and it would probably decrease. So plugging in f prime of 2, we get -12, -4, -5. So it does decrease. Okay, so this is called the first derivative test. This is not used very often at all. Okay, sometimes it has to be used, where we keep this in our back pocket, but this is not what I would do to verify if that's a min or a max. So based on the first derivative test, 1/3 was it a min or a max? So let's
I don't know.
let's kind of make a sketch here.
It was a max. It was a max.
At 1/3, like to the left of 1, it's decreasing at 0. And after 1/3, it's increasing. And then after this is 1, this is 1/3. So 1/3 looks like it's a min, 1 looks like it's a max, right? That's based on the first derivative test. Again, that's not what I do, but that's one test that we have. A better test would be to check the concavity. So concavity means whether it holds water or sheds water. Right here, would you see that it holds water?
Yes.
Okay, right here it's going to shed water.
Yes.
So kind of like if it opens up, it's concave up. Opens down, it's concave down. And we have a negative first derivative, like right here, and then there's another first derivative, there's another first derivative. So how would you describe, as I go to the right, what's happening to my first derivative at that point?
It's smaller.
It went from here to here to here. Is it getting smaller?
Decreasing.
Is it increasing?
Yes.
On a
The
number
whole
line.
time.
On a number line, yes.
That's right.
Like,
Because it is a large negative number, small negative number, eventually 0, small positive number, larger positive number. So in that interval right there, the first derivative is increasing. So if the first derivative is increasing, first deriv increasing, what could we say about the second derivative?
Positive.
Maybe decreasing.
If a function is increasing, what do you know about its derivative? It's positive. So this first derivative, if that was the function, if it's increasing, what could we say about its derivative?
It's negative.
It's positive.
It's positive, it's increasing.
Yeah.
Okay? So the second derivative of the original is positive. Okay, so the definition, if it's concave up, then the second derivative is positive. Okay, as we get close to here, here's my derivative. What's happening to it?
Decrease.
The first derivative is decreasing. The tangents are decreasing. So that would be concave down. The second derivative is negative. Okay, so it looks like they're increasing to about like right here, and then they start to decrease, right? You see that? At some point, it's going to go from increasing to decrease, and that's called an inflection point. Inflection point. It's not concave up or down. Generally, the second derivative is 0, or second derivative is undefined. And it also has to change concavity. So it has to meet one of these, and it also has to change concavity. On one side to the other side, it has to change concavity. All right. So I'm kind of teaching a lesson within one problem. So where are we with this problem? We know if we go back to our potential extrema, a better way to determine whether those are mins and maxes is just to plug those in to our second derivative. If I plug it into the second derivative and I get a positive, that means I'm concave up. And if it's concave up, are we looking at a min or a max?
Min.
It's a min, because it's concave up. If you plug this into the second derivative and you get concave down, then you know it's a max. So let's find our second derivative.
Can we use this for 4.2 then?
No.
If we know. Never mind.
You could if you want to.
Because then you can figure out whether your critical point is.
Yeah,
min or
because
max.
4142, I told you you could use your calculator because you didn't know these.
Yeah.
So if you want to, you can.
Wait,
more
And when it
analytically.
says when it says find analytically and you don't graph it, it would help to know if it's a min or a max.
Right.
Okay.
So in the problems where it said you had to use analytically on 4.1, 4.2, we like use our calculators?
Yeah, well, no. I mean, you would find the derivative, set equal to 0, find those points. Find whether the derivative is undefined, do all that stuff. But as far as the sketch and whether the mins and maxes, then you would use your calculator. Alright, so our second derivative is negative 6x plus 4, right? Let's find whether that is a min or a max. So we're going to do f double prime of 1/3. This is called the second derivative test. And we get negative 6 times 1/3 plus 4. We get negative 2 plus 4. We get 2. And all I really care about is whether it's positive or negative. And at 1/3, it is positive. Therefore, it is a
Concave.
Uh,
concave up, therefore it is a
Minimum.
min. Okay, now f double prime of 1 gives you negative 6 times 1 plus 4 gives you negative 2. That's negative, therefore it is a max. Alright, and so this is the second derivative test, where you plug those into the second derivative and tells you the concavity.
This isn't too bad yet.
How do you suppose you find inflection points in this problem?
Set the second derivative equal to 0.
Very good. So if we set the second derivative equal to 0, so x equals 2/3. Okay, so at 2/3 right here, that's where it's going to change concavity, which we knew happened, and we just found out where it happens. If you plug a potential min or max into the second derivative and get 0, then it's inconclusive. It's maybe, it might still be a min or max, but
How could
We'd
it
have
still
to
be a
use-
min or a max?
if the graphic ends, maybe.
Oh.
So if it doesn't work, if you get 0 into the second derivative, then you'd have to use like a first derivative. Or just plug in to the original and find y values in that region. You can find out if it's a min or a max. Okay, so let's start answering some questions. Inflection point, we only have one. It is at 2/3, comma, something. I want your y values for the inflection point, always. Inflection points always require a y value. So how do I find the y value here?
The second derivative of
Plug it into the original equation.
Plug it in the ridge. We just want to know what that y value is right there, yeah? So
second derivative.
f of
That would be
2/3.
like the slope of the slope, but you just want what the y value is.
We just don't know what that y value is, so
Oh, okay.
f of 2/3 is, I'm not doing that.
16.
I gotcha.
I'm being filmed, I don't want to be embarrassed.
Would it be cool?
Somebody's working that. Derek's working on it.
Yeah.
Okay. We could do increasing and decreasing. Where does it increase?
Did you write this somewhere?
From 1/3 to 1, right? If I'm going from a min to a max, I'm going to increase. So in the interval notation, I'm going from 1/3 to 1
I think I got it.
is increasing. What'd you get?
Is it 1.51?
Yep, that's what I got. No, wait, I got a positive. Well, it might be a negative. I just drew this arbitrary. So is it negative 1?
Yeah, negative 1.51.
Good enough. All right. Decreasing
Negative infinity to 1/3.
from here all the way to there. And then also 1 to infinity. Extrema, I've got a relative max equal to, we don't know what the max is there. How do I find what the y value is there? Plug 1 in. We could maybe do that one. Negative 1 plus 2 is 1. Minus 1 is 0.
MI is
1?
0.9.
Okay, I was like,
So relative max is equal to 1 at x equals 1. And it's a relative min equal to 1/3. Negative 1/27 plus 2/9 minus 1/3 plus 1 is? Bailey, did you get it in your head? No, me either.
Well, I lied. It's 0.9.
This one was 0.9?
Yeah. Also 0.9.
Okay.
Because the negative and the negative.
Will you plug 1/3 in? The 2/3 was 0.9, I think. Thank you. And that's 0.85 at x equals 1/3. By the way, are are either of them absolute mins or maxes?
No.
They're both relative, right?
Do you have
Alright,
do you have to say whether they're relative or absolute?
for right now you do. Probably by the time we do the test, I will accept all just relative.
So when you do quiz, can you like make it so that the answers like clearly ask for?
Yep.
Okay.
And if you're unsure, ask me.
Will it have a range or a domain? Like a inequality where x is.
Maybe. Okay, last thing we have to do is answer whether it's where it is concave up. It's concave up everywhere on the left side until we get to the inflection point, which is
2/3.
2/3. So it's concave up from negative infinity to 2/3. That would put it concave down from 2/3 to infinity. Alright, so we're confident nothing else significant happens to the graph outside of what we have done because our algebra and calculus supports the fact that those are the only interesting points on the graph. Okay, it gets a lot more gnarly as far as derivatives and stuff like that goes. I don't know if you've looked in the notes, but there's a whole page problem where you have to find the second derivative, plug it in, and it just a lot of work. So that's the process. I don't think is that bad. Find the first derivative. Should we write this down? First derivative, and then you could set it equal to 0. Find potential extrema. So basically, remember the 3 or 4 step process that I told you before how to find extrema? That 4-point. All of that is part of this process. So set the first derivative equal to 0. Solve, find where the first derivative, like the bottom of the fraction, where it's undefined. And check endpoints. All of those are finding extrema, mins and maxes. Okay, then you have to find the second derivative.
Should you check to make sure it's not a horizontal tangent?
Check to see what?
If that is not a horizontal tangent, because then it would be a min or a max, but there would still be 0.
That would actually show up in the second derivative, because if you plug it into the second derivative and get 0, that'll tell you it's an inflection point, probably not a min or max. But you might have to come back to that, like y equals x cubed.
Oh, that spot in the middle.
Yeah.
If you plug that into the second derivative, you're going to get 0, which tells you that
Okay.
it's not a min or a max. Probably. I don't know if that answered your question or not.
I guess.
Find second derivative. You can set it equal to 0 to find inflection points. And probably use second derivative test. To determine mins or maxes. Is that what we did? Okay, so that's a polynomial. We knew kind of the shape of a polynomial. It's a cubic with a leading coefficient negative, so we knew that this is what it would look like. If you looked at y equals x squared square root of x plus 1, I'm guessing most of you don't know off the top of your head what that graph would look like. Y equals x squared square root of x plus 1. Okay, so to analyze this completely, without any knowledge really of the shape of the graph is quite a bit of work, as you can see from this page. So I'm not going to go through every step, but you can see the first thing I did is find the derivative. Are you following along in the notes now? I'll give you a second. Once you grab your notes, and I'm just going to kind of talk my way through this problem. Because really the toughest part is the algebra. Alright, so we found the derivative. I cleaned it up. I set it equal to 0. I moved one of them to the other side. Looks like I multiply both sides by the square root of x plus 1. Oh, and 2. So multiply by 2, square root of x plus 1. Ended up getting a quadratic, so you get two answers, 0 and negative 4/5. So those are your potential extrema. Second derivative, looks like a lot of fun. I did quotient rule. Combined the last two terms, set equal to 0. Oof. Cross multiplied, and looks like there's one inflection point, negative 0.47, comma 0.16. The other answer to that is not in the domain.
So that's if you don't graph it.
Right.
Is there a cheater's way to graph it to check your work? Like,
You won't get graphing calculators on it.
oh. Everything I asked.
We're down here, and then 1, it's up here, so I know what the tendency of the graph is. I know I'm going to go from here up to here. I know that this has a horizontal tangent, and then it goes down. So make a sketch at some point once you have enough clues, and once you have a sketch, the whole increasing and decreasing is pretty straightforward. The concave up and down is pretty straightforward.
I feel like labeling whether or not it's F prime or F double prime would be helpful too.
Wait, so like, is there any point on F where F prime or F double prime is equal to 0 where it's not an inflection point?
Yeah, if it's at the end point, it has to change concavity, and if it's at the end of the graph, it doesn't change, just stops.
Okay,
So I'd have to think about what that would be.
So would you want us to put endpoints as inflection points?
No, not if it's an endpoint.
Okay.
Yeah, that was a question in the AP conference. Somebody, the calc guru said, well, here's a problem. If you know that the second derivative is 0 at this point, what can you safely conclude? And all the calc teachers like me said, well, it's probably it's an inflection point. And then he tricked us all because, you did not check concavity on both sides. This is not necessarily an inflection point. On the AP exam, you would lose 2 points. Because you didn't support your answer. Even though it might have been an inflection point, you have to verify that it's an inflection point by checking concavity on both sides. Did we check concavity on both sides of our inflection point here? We did by finding the mins and maxes, right? So it's done. We're safe and confident that it is an inflection point because it went from concave up to concave. All right, that's all I have to say.